Yeah, good evening, everyone. So today is the third session uh, of the software PSSe. So let's just have a quick recap of last two sessions, and then today we'll see about automation feature in PSSe as well as how to perform a short circuit study. So let us start with a recap. So as we know, we started from with an example. So let's just open that example first. Again, this example is taken from the Power System Stability and Control book written by Dr. Prabha Kundur. So let's just open. Yeah. So this is the system which we like to simulate, which we like to analyze. So first we saw that how to enter the loop flow data or network data of this system. So let me just load it again. And let me just solve it again. So as you can see, the load flow is converged, and again it's just a recap. So we can verify it with the data given in the textbook that generator 3, we chose generator 3 as our slack generator. So the P generation is uh, is 719 and the Q generation is 176. So it is matching with the data given in the textbook. So our load flow is converged with proper output. Now the second thing is that this is okay with for the load flow study. Now for the dynamic simulation for a time domain simulation, we again have to load the dynamic data of the system. So dynamic data for generator especially. So as we that also we have done in the second session. So that data is in that .dyr file. So let me open it. Okay, and yes, so here we have generator data, exciter data. Then we also have provision to add turbine governor data as well as stabilizer data and other relevant data. So as far as this system is concerned, the only dynamic element in this system is generator. All the load and everything which is modeled as constant impedance load. So there is no dynamic element there. And yeah, so let's go with the generator. So one thing we that was remaining for the last that was remaining in the last session, that is saturation factors. This row 13 and 14. So basically, generally in all commercially available software such as PSSe, the saturation data was entered like in a 2 point form. So we only have to give 2 points of a curve, and based on those points, it will automatically calculate the entire curve. Fine. So here we have to give 2 points, S1.0, S1.1. What it means is that at open circuit voltage of 1 per unit, what is the value of S that we have to enter here? And at open circuit voltage of 1.2 per unit, what is the value of S that we have to enter here? So how to calculate the value of S 1.0 and 1.1? There is a meaning of it. Now how to there is a saturation factor. S means saturation factor. So how to calculate it? So the simple formula is this. Like, let's say if we have given the saturation data in this form, that the value in exponential form, where we have given the value of A set, B set, and psi T1. What it indicates that up to point 0.9, up to the flux linkage being for 0.9, the characteristic is linear, and then it becomes non-linear. I mean, the saturation occurs only after psi become more than 0.9. Okay, so 0.9 opens this 0.9 psi, or in per unitation psi and V, we can assume it to be equal. So this voltage also we can think like of 0.9 per unit open circuit voltage. So up to that the characteristic is linear, and then the saturation will pops in. So basically uh, yes, basically this S 1.0 and 1.2, that indicates that how much saturation is there. So the formula I'll just write it here. So we have A set, which is 0.015. Then we have B set, that is 9.6. Then we have psi T1, which is 0.9. Now we want two values, psi S1.0, S1.1. So our psi, sorry, yes. So our psi 2 is 1 and psi T3 is 1.2. I mean, at these 2 points, we want to get the value of S. So let's just say S1 is the equation is A set into E raised to B set into psi T2 minus psi T1 divided by psi T1. Sorry, psi T2. So this is the expression for S1 and this is the value of S1. So this is the value we have to enter there. Now S2, so again very similar to S1, only thing we have to replace is instead of psi 2, psi T2, now we want the value at psi T3. So this is the value of S2, means S1 means S1.0, S2 means S1.1. Fine. Now one thing which we have to just remember is that the saturation factor is basically the indication of how much the core is saturated. Fine. So S1, S2 should always, I mean, there's a cross check. So S2 should always comes out to be greater than S1. That is one cross check. That if S2 is greater than S1 means that is one of the cross check to verify it. And higher this number indicates higher saturation. So at 1 per unit, we can see that number is smaller. So there is a little saturation there. And at 1.2 per unit, open circuit voltage, we can see the number is quite high. So it means there is a high saturation. So these 2 points we have to indicate. This is the cross checking. I mean, this is how you can cross check that whether it is correct or not. Fine. So now we'll enter these two values into the PSSe. So S1 is 39175. S2 is okay. Now same thing we have to do for all, because as you know the saturation is same for all the models. Okay. So this is just a recap of what we have seen last time. And now let's see some other feature, other very useful feature of PSSe. That is the automation feature. It means like every time if you follow the last two sessions, you come to to perform every task. We have to do multiple clickings. I mean, we have to select multiple options and then you want to perform a simulation with multiple operations. Every time we have to stop the process, then we have to initiate the fault, clear the fault, and then again start the simulation and all. So it will take long time, especially if we want to do simulation in a batch mode. Let's say we want to create fault at multiple locations in a sequence, or let's say we want to see the, or we want to if we want to calculate the CCT, the critical clearing time of a fault, then we have to do multiple simulations, or we have to do simulations in a batch mode. So every time changing the setting and starting from scratch, like I mean doing like one by thing, it will take longer time and it's not very efficient. So one good facility or the good feature of PSSe, that is PSSe is fully integrated with Python. What I'm trying to say is that if you have Python installed, then just by using the Python, you can operate all the or you can use all the functionality of PSSe just by command line. So you can write a program, just save it, and just by changing parameter there, or making a loop or any kind of logic you can build there, and run the multiple programs or multiple routines in PSSe using Python. So again, that is actually a very big facility, and so many functionality and functions are there. But as far as our this today's session is concerned, we'll just give you index. I mean, we'll just give you some highlight of that feature, and later one can explore here. I mean, in the documentation, if you just go, then there is automation documentation is there, where you can find when you can learn and you can implement complex algorithms or complex implementation to perform different tasks. But let's just get a simplest, very simple program. Let's just build a very simple program. But the thing is that we don't know what command to write to perform certain application, or let's say to perform certain task. So the very good feature here in PSSe, that is the record function. So we can enable the recording, and then whatever task or whatever action we perform, it will record it, and then later we can reuse it. So let's just start from the scratch. I'll just I'll just close it and then reopen it to show you how it saves all the steps and all. So I'll just close this PSSe. I'll reopen it. नहीं वो दिखता है. Yeah, till it opens, like if anyone have any question regarding the first two sessions, like regarding load flow or regarding dynamic simulation, we'll just take, I mean, just have to wait till it opens. It opens two times. I'll just close one. Okay. So now before doing anything, let's just start the recording. So here you can see this tab, this red button. So that is for start recording. Fine. So we first have to enable it. So let's just start recording. We have to save the file somewhere, and we can give any name. So let's say test run 1. Fine. Save. Okay, so now whatever action we take now onwards, it keep on having the record of it. Fine. So let's just open the row file again and let perform the load flow. Done. Now let's convert it. Convert the load and generator to go for dynamic simulation. Done. Now let's load the DYR file, dynamic data file. Done. Now if you recall, so before performing dynamic simulation, we have to select or set the channels. So let's just set the channel first. So basic, I mean, let's have all the basic function, default function as it is, and we want to monitor for all buses. So done. Close. So you can see channel is selected, proper channels are selected. Next thing is in the simulation parameters, we can set this delta t, whatever value we like. So currently it is 10 milliseconds. So let's just keep it there only. 10 millisecond. Simulation time step. Okay. Now in the simulation, perform simulation, we have to save out file or the output file. So let's just call it run one. Fine. Save. Then we have to initialize it. So initialize, initial condition check, okay, means initialization process done appropriately. Now I'm giving print every 1000. This is the maximum value we can give. So 1000 means I don't want to print every time, like every time step output here, because then it will take a lot of time to do the simulation. Okay. Okay. So now we'll run it for 1 second. So run to 1 second, run and complete. Now let's apply a fault. Bus fault at bus number 5. Bus number 5 means here. Fine. Let's apply a fault there. A default solid bolted fault. And that fault up to 100 milliseconds. So let's run to 1.1. Done. Now in the dynamics, let's clear the fault. And now let it run for 20 seconds. And done. Close. Fine. So we done the procedure, and whatever action we took, it's been saved. So let's stop the recording. So this is stop recording. Done. Now if you open the file which we have saved, that is test run one file. Let's open it into Notepad. Okay. You see now all the steps which we took, it came here. So first we open this uh, network data file, then we perform the load flow. So this is the command to perform the load flow. Now again, if you visit documentation, you will find all this command, what are the settings, what are the different parameters, what are the different settings of this commands or this function that you can go through. I mean, you can check there. But this is this set of command is the command which we done right now. I mean, this is the steps we followed right now. Okay, so this is for load flow. Then this is for that conversion. Then we load dynamic file. Then we set the channels, output channels. Then again we start the simulation. Then initialization. Then we run for 1 second. Then we apply the disturbance. Then we clear the disturbance. So all the steps are here. Fine. Now we can save it. We can modify it. We can alter it, and we can get whatever we want. Fine. So let's just modify this, and we'll see like how output changes. So let me first open the output. So this run1.out is the output file. run, and we can see all generator speed, angle, everything. So let us plot the speed. So this is the response we got after applying fault at bus 5. Now let us say we don't want to apply a fault at bus 5. We want to apply a fault at let's say bus 6. Fine. So first were to give that bus 5 or 6, and that information either you can get from looking into the manual, or you can change it one time. Let's say instead of 5 you change it to 6, and you come to know, okay, now this is the change. So let me give you an example of that as well. So again, start the recording, give some new name, let's say temporary one, save, and then apply the disturbance. Bus fault, select 6, okay, okay, and then stop the recording. So, I mean, I'm just giving you some head start. Let's say you don't know anything, you don't want to dig into the manual file, or say you want something very quickly. So, this is one way to get it very quickly. And if you open it, yep, this is the command to apply the fault at bus 6. So, if you compare, you see this is that number, the bus number. Here it is this 5. Apply disturbance 3-phase bus fault 5, 6, whatever. So now if you want to do it, let's say in a cyclic manner, multiple times. So what you can do, you can just make a for loop, then save it in a for loop and perform the same task 3 times, 4 times, 5 times like that. Okay, and this is a Python file. This is .py file. So you can use all Python functions here for a loop, for a logic, for whatever. Fine. So let me just change from 5 to 6, and this output file which we have which we have saved as run 1, let's change it to run 2. Fine. So the output file now is run 2, and in this simulation we want to apply the fault at bus 6. Fine. Save it. Now we'll run this file. So again, PSSe. Now here you see this run automation file. You have to click it. Then you have to select which file you want to run. So this test run 1, this is the file which we have modified. So we just have to select it and open. And done. You see, it is performing and done. So it load the network file, network data again, it load the dynamic data, it perform all the tasks, apply the fault, clear the fault, everything. And it save the run 2. So this is run 2, run2.out. See, we have to open it. And yes. Yeah, yes.
We run this Python file from Python.
Yes, we can run the Python file for Python as well, but then we have to first invoke the PSSe there.
Yeah, like import libraries.
Yes. So as I said, I mean this functionality is like if you have PSSe open, you can run any Python file here. But if you have Python open and PSSe install in your system, then from the Python itself also you can open the PSSe, run the PSSe without opening this GUI. Without opening this GUI, you can perform or you can run the entire simulation natively in Python itself. In the background, it will open PSSe and perform the background task, but you do not need to open the PSSe GUI. Fine. So that is one thing. So yeah, it's a very powerful functionality. I mean, from the Python, you have all the functionality of Python programming, all the functions available to you to perform, to operate, to analyze, as well as you have all the powerful functions of PSSe as well. Only thing you have to remember or you have to keep a track is these functions, like to call which function to perform which task. That's all, nothing else. Fine. So yeah, so I mean, this is just an overview. This is just an. I just gave you
one question.
Yes.
Now, if I want to change this clearing time, it was 1.1, right?
Yes.
So I have to change. I want to change it for by some around. I have to just find critical clearing time.
Correct.
So I will make sure that there are multiple output files.
Yes.
But is it possible to open means to identify after which point it is getting unstable
Yes.
rather
Yes.
than opening it in PSSe?
Yes, correct. So whatever output file we saved, we again have option to extract that data. Fine. So here itself, I mean, via coding itself, you can extract the data. You can set some threshold. When you say critical clearing time, means we can set some higher threshold. Let's say angle going beyond this or like that. So we can call it unstable or something like that. So we have access of all the data here.
So you can open that.
You can open the out file. Out file is not a text file. It is a binary file, but using PSSe function, we can open the file, extract the data, use the data, basically. Not directly by double clicking, but via coding, there are functions available.
You again have to invoke the PSSe.
No, 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 no.
Can you just give a right to file? Can you whichever location can you just from outside, like from the direct?
Here.
No, no. Folder.
As a folder, okay. This folder? This out file.
Yeah, you can't open it in.
Yeah. Okay. Let me show you. Let me show you by opening it into a notepad. What you'll see. See? It's a binary file, so you cannot open it in notepad. But there are functions available. So I'll show you from the internally of the PSSe, but the same thing you can do from the programming. That is, if you just right click, there is an option like export to Excel, export to text, like that.
So that particular waveform can be exported to
all the data you can export. All the data, entire data you can export.
probably what I understand is if you keep the recording on and if you do right click and export, I think that will be also okay.
And there are some inbuilt functions also available to detect this out of swing and all. So again, one have to dig into the manual. There are so many functionalities. All the functionality which you are seeing here, all the functionalities are accessible via the automation. So you just have to select a particular functionality, find a command for it and use it appropriately. Let's say here also, if I right click, you see this voltage violations, then filter channels. So all scan results. So all the functionalities are there. So this you have to just find a function for it, or maybe record it and use it once, and then modify it as per your need.
To automate it, we should put a filter, kind of filter that after this angle reaching this point.
Yes, correct.
Don't do it actually.
Correct. Don't perform the run and all those things. Yes, yes, yes. So even in simulation also we have multiple functions available to check this out of sync and all. So it can detect, it can give you a warning, it can stop the simulation. All those things is possible inside. I mean, all the functionality. Even if you see the option here you see so many options which you can enable for better simulation. So voltage violation. So you can set like after how much voltage violation you want to stop or you want to flag or you want to get the error. So all those functionalities are there. Fine. So that you can explore, and whatever functionality you can see here, all those functionality can be accessed via automation. Only thing is that one have to identify the function or the function name and the function string from the manual and use it. That's all.
The manual is a CPI
Command line. You know. It's fine, right? Yes. So yeah. So I mean, we just scratch the surface of this automation. We just show you like it is possible, and we just give you one simplest example to do it. But later one can explore the manual or maybe over the internet because so many help is also available. So many for different forums. Help is available to do different kind of automation studies and all. So later one can explore. So yeah, this is it for this automation part. Now Rohit will present the short circuit study, how to perform it, how to set the data and all. Okay, hand it over to Rohit.
So good afternoon. I will be showing this short circuit study using PSSe. There are some 2 to 3 routines we can use to do short circuit studies. So basically, we'll check how we can do it using the same example which is already there in PSSe. So first we will open the example. You must be knowing the RAW file. So we are using so you are familiar with this data where we can perform load flow, power flow. Okay, so you know how to obtain these values using power flow routine in a PSSe. Now, first we will check how many options are available in short circuit right now. So some of the options are not available still. We'll check first automatic sequence fault calculation. So here first we can set some options to pre-fault conditions. You must be knowing how to obtain a short circuit means in fault analysis. We assume some initial bus voltages at the starting, and then we will check how the fault current injection at a fault bus changes the bus voltages, and accordingly the current distribution across all the branches. So there are some options. First, we will see how the default means. According to this option, all the remaining options changes. So one by one, we will check. We will check the three-phase fault first. Um, First, we can see fault current summary or fault current with Thevenin impedance. Thevenin impedance is the diagonal element of the Z bus matrix. So again, the option is to change the tap setting and angle of it. Generator reactance, usually we take sub transient, line charging, leave unchanged, shunt, which are modeled in the system, or loads. So all of them are unchanged. Basically, we are having a load flow means detailed short circuit, which is different than what we use in a flat classical assumption, where all the pre-fault buses are 1 per unit, angle 0. So we'll just run.
Line charging and what all options are there?
So we can put positive sequence, negative sequence impedance to 0. All sequence means there. First, we don't have any sequence data of this file. We only have positive sequence. So we'll just put a run for a bus fault at 151. So all those options are means option used for the fault analysis are written over here. So we used power flow solution, means the fault is fault considered this voltage for fault analysis as a primary pre-fault voltage, and then the change due to fault is added to that value. So this is the three-fold short circuit MVA, and these are the real and reactive component of the fault current. And the Thevenin impedance, positive sequence Thevenin impedance is this value. Similarly, let us see how a flat classical assumptions changes the output. So again, the same bus. Now these options have been changed. All the shunts are kept to are made 0. So you can see there is a phase shift in fault current, and the magnitude is less. So this is a symmetrical fault, three-phase fault. Now let us for an unbalanced fault or unsymmetrical fault, we need sequence data of each component. Now you can see in the machine data is absent. This zero sequence, negative sequence, transient, subtransient impedances are not there. Again, in branches, zero sequence impedance is not there. Transformer, we will check how these values are modified after loading of sequence file. So now let us load the sequence. If you see, there is no value there. They are just empty. This example is from this folder, so it is available to all. So now you can see all the data. Let's start from machine. Negative sequence, transient, subtransient, transient synchronous impedances, negative zero sequence impedances are now defined. Again, this zero sequence of line, and in transformer we have this vector groups of this transformer. Those are also now uploaded. So usually for generator transformer, high voltage side is star and low voltage side is delta. So 500 kV and 21.6 kV is delta. These are important for sequence component because their connections make major difference in sequence components. So we'll see how they are defined. So here you can see connection code. So it is 2121. So more detail on it is given in this manual. So if it is star, the connection code is 1, delta star 3. So accordingly, you can modify the connection code whatever is required. Generally, this data, the sequence file can't be open outside. So you can export such data for reference using list data. So sequence data is here for all buses. All data is selected. So this is all sequence data. You can access it outside. You can save it in Notepad, txt file. Okay. So next we go for now the options are all options are available in this short circuit studies. So we will go for a unbalanced or unsymmetrical fault analysis. So again, the same options: flat, classical, or default. We will apply this. The option is line to ground fault. Again, we will give. So for asymmetrical fault, we have positive sequence Thevenin impedance, negative sequence, and zero sequence Thevenin impedance, and this is the fault current. So let's increase the information we can see in the output. So there is another option where we can see the contribution from n level behind, buses from n level behind. So let us see, make it 1, the level 1 behind. So at bus 151, it is connected to, let me show you the diagram. So 151 is connected to 101 through generator transformer, 102 to 201. So these all contributions are given there. So first, it has positive sequence, really complex value of positive sequence, negative sequence, zero sequence, and 3 times of negative sequence. So, and again, we have phase A, phase B, phase C recalculated. So this is the fault current. These are the contributions from each bus. So this is the detailed output. And again, now let us see 151. So what are the contributions to 101? At 101, there is synchronous machine and there is a transformer. Again, means what are the injections at this point? So these two are again in positive sequence domain and phase domain. Similarly for all the contributions, and that too 1 level behind. So next thing is I see there is another routine where you can use this option to calculate the fault currents using IC 60909. What is 60909 is, they give a, we'll have some. So basically the impedance of AC system components are corrected as per. So these standard provides a correction factors for impedance. The procedure and more details are given here. So each generator, transformer and all are multiplied with some factor, and there is a procedure to calculate it. So basically after calculating, the PSSe will do this for that routine IEC. We'll check how it done that. And basically it also gives, when we do a time domain simulation, the fault current is like this, near to generator, where there is a DC component, the envelope is also reducing. So with the same data which we have defined in the PSSe, we can calculate these parameters, the same parameters, using some correction factors and all. So those are also there. So we'll check first that. So again, the same fault current. Now for more component of that current, you select total currents with Thevenin impedance. Now there is symmetrical short circuit current, then peak value using method B. So there are some methods to calculate the peak value. So this is the peak value, IP. there are methods to calculate it: peak short circuit current, steady state short circuit current. So those all are all mentioned here. DC component, unsymmetrical, symmetrical component are there. So this is required for various purpose, like for designing the for calculating the circuit breaker current breaking capability and like that. So this is the same thing. And again, the rest of the things are similar to the ASCC, which is automatic short circuit calculations.
If you see
Ah,
the option which you have chosen, the option following buses they have made. So is it like वो देखो last option में following buses लिखा है.
हाँ.
वो ऐसा है कि एक साथ जैसे
No, this is all individual. If you do like this, let us say, I will select all buses. Okay.
so individually one at a time.
One at a time it will solve. So these are all buses and these are all single phase currents. So simultaneous fault is another routine. We will check that also. So this is IEC according to IEC standard. The next is this multiple simultaneous unbalances. So here you can include these unbalances. So let us say first single SG at 151 phase A, this is selected. 154 phase B. So so first it will say what are the unbalances it has applied. These are the Thevenin impedances in sequence domain, 0, positive, negative. These are the voltages at this value. So when we are applying a single line to ground fault, phase A value should be 0. So for bus 151, phase A is 0, and similar to previous output, it also gives the current from the level 1 buses. Another so
here you are applying multiple fault at
simultaneously.
All are LG fault.
All are LG fault. We can change. So at 154 phase B is 0. So both fault has applied. So the contributions to that bus, addition as sum of the contribution into bus plus or minus load currents, and this is the fault current. Okay. And again, if you want to see what are the currents coming to any bus for this solved case, let us say 152. So it can give currents, apparent impedance, apparent admittance. Apparent impedance is something which they have defined in the manual, so you can check it. So these are all options we explored this here. These are not yet, means I have not seen those in detail, so I will not check this. So,
and I think
any questions?
Automation, actually, whatever you do here, automation.
Yeah. All things can be done.
Okay.
So little bit.
Please let us.